I encourage everyone to go through and go through the extra workshops, the extra tutorials and website page, and go through their tutorials, their simulations, there are extra worksheets. So I suggest you guys go through that page and get some info, get some extra information there. So yeah, I think that will be very beneficial for you if you use those extra. Yeah, unit 4, and it's a foundational unit as well. So if you don't get if you don't if you're not able to get the information from this unit, then it's going to be hard moving forward when we're looking at chemical reactions and that sort of thing. So it's really important that you get this foundational unit. So tonight, the problems that we're going to work on are looking at Lewis structures, intermolecular forces, polarity, and molecule shapes. So that's what we're going to work on tonight. All right, can you guys see my screen as well?
Yes.
Do you see the Zoom window with you guys in it too? Or is that just what I see?
No.
Okay, cool. All right. All right, I'll give you a little while longer for this question. I'll give you a 60-second timer. So write your answer. All you have to do is use the format that you see there. C, number of carbons, H, Br, Cl, and you're just writing the formula based on the number of each of the atoms that you see in the image. So I'm gonna add the numbers in after I close the question. We've got another 15 seconds. If you didn't get it now, you can make sure to answer this question later. 5 seconds. All right. So based on the image that we see, there are 2 carbons. There are 2 carbons. There are 2 hydrogens. There are 2 bromines and 2 chlorine atoms. So your formula should be C2H2. Well, it's going to look like this. C2H2Br2Cl, well, 2. Okay. Let's see. All right, the next question is going to be a Lewis structure question. Here you're going to select the one that is not correct, the Lewis structure that is not correct. You guys want me to send you in your groups for this one? I'll break you out for this one. create. And I will send you for about 3 minutes. You can check with each other. All right, guys. So let us close out the answer. Let's close out the question. Let's see what your responses are. The majority of you got this question correct. So if we were to take a look at the Lewis structures for each of these ions and compounds, we notice that for ClO minus, there are 14 valence electrons. If we place our first pair of electrons in between each one, and then we add on the rest, so that's 2, 4, 4, 6, 8, 10, 12, 14. We could leave that just like it is because everyone has an octet. How do we know that everyone has an octet? Is because this is a shared pair of electrons. That oxygen has its octet, the chlorine has its octet, and remember we have to have our minus sign. If we take a look at cyanide, it has 10 valence electrons. We place our first one in between the two atoms. That gives us 2, 4, 6, 8, 10. We have all 10 electrons. But notice that carbon only has 2 pairs. That would mean that it only has 4 electrons surrounding it. So we have to borrow 2 pairs of electrons from the nitrogen so that now carbon has an octet. And how do we know that it has an octet? Is because it's sharing those 3 pairs of electrons, and the nitrogen is sharing those 3 pairs of electrons. And just memorize water. Just memorize it. Water, oh wait, was this water? No, it wasn't water. It was hydronium. So I didn't do that one right. So 1 times 3, so that gives 6, and then minus 1 electron. So that's 3. It's still 8 valence electrons, but I need a hydrogen there. Did I do that right? No, I was definitely looking at that as water. So hold on. I've got 3 times 1. Oxygen has 6, and then I have to subtract 1. So 3 times 1 is 3, plus 6 is 9, minus 1 is 8. And I've got oxygen, hydrogen, hydrogen, hydrogen. 1, 2, 3. That is 6 electrons, and place the last one on the outside, and that gives me a plus 1. So the one that is not drawn correctly is B, because it has too many lone pairs of electrons on nitrogen versus where it should only have 1 lone pair. So the answer is B.
Professor,
right?
can you explain why again?
Can I explain which one?
Can you explain why B is wrong again?
Oh, okay. So if you look at the answer for B, notice that B it's got 2 lone pairs of electrons here, where the actual structure only has 1 lone pair and 3 bonds. So here, the reason why is if we count the number of electrons on carbon, there's 2, 4, 6 electrons on carbon, but there are 8 electrons on nitrogen. So we have to share an additional pair of electrons to give that triple bond. And that's why. Got it?
Okay. Yeah, I got it. Thank you.
All right. So let's take a look at the structure here. If we look at the Lewis structure of carbon dioxide, we've got 4 bonds. Each bond, remember, represents 1, 2 electrons. So how many electrons are surrounding the carbon atom?
8.
8. Are they bonded or are they lone pairs?
Bonded.
They're bonded. If we look at C, C says it has zero lone pair electrons and 4 bonded electrons. No, if it said 4 lone pairs, 4 bonded pairs of electrons, then that would have been right. So the answer is A. Yeah, this unit will definitely, it will definitely take you out. You've got to really, really go back over these problems, do all of the practice problems in do all of the practice problems that you see in the practice problem page, as well as, do as many of the tutorials and that sort of things. So the next question is posted. I'm going to send you back to your rooms. Give you 4 minutes to work. Is everybody back in the main room? You want a couple more minutes to work?
Yes, please.
Yes.
All right, guys. Let us take a look at the answers here. So if we're looking at the first one, SCl2, notice that we've got 1, 2, 3, 4 electron groups. That would give me tetrahedral electron geometry. However, I only have 1, 2 atoms attached, so that would give me a bent shape. Bromine is simple. It's just one bond but 2 atoms. It's gonna be linear, a linear shape. Looking at SO2, so sometimes you'll get like an idea of how things will always, like everything in the same group is going to make the same types of bonds. So like for SiH4, it's going to have the same shape and everything as CH4 because silicon and carbon are in the same group. So you don't necessarily have to, once you figure out what the shape is for CH4, you can always figure out anything else in that same group has the same type of shape. So SiH4 is going to be tetrahedral electron and molecular geometry. So for SO2, can you guys see my mouse moving?
Yeah.
Okay. So for SO2, there's more than one way that you can draw it, but it's going to have 1, 2, 3 electron groups surrounding it. So that's going to give us the trigonal planar electron geometry. But being that I only have 1, 2 atoms attached, that gives me the bent shape. And last with BCl3, we've got 1, 2, 3 electron groups and 3 attachment. That means trigonal planar for all for the, what am I trying to say? Trigonal planar for the electron and molecule geometry, and HCl is going to be linear. This is very similar to the Br2. Okay?
Professor, sorry to interrupt. By electron groups, you mean bonds?
No, I mean electron groups. So let's look at SCl2. I've got 1, 2, 3, 4 groups of electrons surrounding my sulfur. Only 2 of those groups are bonded. The others are lone pair. So it doesn't matter which one it would be. I'm sorry, it doesn't matter whether they're bonded or lone pair. So the question, why wouldn't HCl be trigonal pyramidal? Is that the question? Pyramidal, I would have to have another pair of electrons up here in order for it to be pyramidal. So in order for something to be trigonal pyramidal, it has to have 4 electron groups, like SO, like SO2. No, that's actually trigonal planar. Let me take that back. It has to have 4 electron groups, like what else can I think of? It would have to have, let's say, XY, right? I have 1, 2, 3, 4 electron groups, which would give me tetrahedral. But because I have 1, 2, 3 bonded atoms, so tetrahedral is the electron geometry. But because I have 3 bonded atoms, that gives me trigonal pyramidal. Because it looks something like a pyramid. Yes. All right. Thanks for sharing the two what am I going to say? Thanks for sharing those 2 images. So this is similar to what is in the, what's in the textbook, as well as what's in your workshop that that we have. So yes, question.
Hi, so this is about BCl3. So I remember from the clutch prep that boron is an exception to the octet rule. Same thing with beryllium, etc. And I was just wondering, like, what the reasoning is for that, or if it's just something we need to memorize.
It's something that, so even if we take a look at boron, let's say we were gonna do this, BCl3, there are 24 electrons. If I put boron and I put my 3 chlorines around it, and let's place all of the rest of the electrons. So this is 2, 4, 6, 8, 10, 12, 14, 16, 18, 22, 24. There are no more electrons to add. So even if you didn't memorize it, all of the electrons have been placed. And this has to do with the fact that boron is in group 3, and it's more energetically favorable for it to have the atoms surrounding it in this way. So even if you never memorized it and you just did the Lewis structure, all the electrons have been placed. There are no more electrons to add to the Lewis structure.
Got it. Okay, so essentially you run out of electrons, and
yeah.
Cool, thank you.
All right, let's see. What question are we going to do next? We'll do this one. So this is another matching set of questions. I'm going to send you guys back out to your groups. If we take a look at CSL2, notice that, so whenever you're doing these polarity of molecule questions, you've got 2 steps. First, you've got to draw the Lewis structure, then you got to determine the shape to see how the how the molecule would look and determine if the shape is symmetrical or not. So for SCl2, we know that this is bent because I've got 1, 2, 3, 4 groups, but only 2 attachments. So this is a bent shape. And if I look at the electronegativity difference between these two elements, I have 0.5, meaning that it's a polar bond. And since the chlorine is more electronegative, the dipole or the pole is going to be facing the chlorine, meaning that the chlorine atom has more share of electrons. And even if you look at the chlorine with all these extra electrons around it, it has more electrons surrounding it than the sulfur. So those chlorines are going to be more electronegative. And being that it's the bent shape, the whole polarity of the molecule is going to go downward. So CSL2 is going to be polar. So you can't just find the electronegativity difference for each one. You have to look at the whole entire molecule, because if we look at something like BCl3, sure, each bond is a polar bond, but guess what? The entire molecule is non-polar because it's symmetrical, right? The same thing for CBr. I was just about to finish writing that. The polarity difference between the carbon, the Cl and the B, C and Br is 0.5. So each one of these bonds is polar, sure, going towards the bromine, because the bromine is more electronegative, but the molecule is non-polar because it's a symmetrical molecule and the electrons are all pulling equally, right? So let's say trigonal planar, linear, and tetrahedral. These are all symmetrical shapes. And it matters. So it would have to be all the same, like each atom attached would have to have the same electronegativity in order for the whole entire molecule to be non-polar. Because let's say I got rid of that one of these bromines here and I put a hydrogen now, even though I have a whole tetrahedral molecule, I mean, I have a tetrahedral shape. Now that over here I've got a hydrogen and not a bromine, that would make the molecule asymmetrical, right? And the polarity would go, let's give it a different color. The polarity would go in this direction. All right. So Br is non-polar, Br2 is non-polar because we've got equal sharing of electrons between both of the bromines. They're the same molecule, they're the same atom. For SO2, this is a trigonal planar molecule in the electron geometry, but the shape is bent. And if we look at the electronegativity difference between S and O, we get a 1. And so the dipoles would be facing the oxygen atoms. So the entire molecule would be polar, facing down towards the oxygens. Yes, so that is a good way to think about electronegativity, that the atoms that are more electronegative, they're greedy and they want to pull the electrons away. Have you ever shared the bed with someone and they're always snatching the covers?
It's the worst.
That's the high electronegativity one, okay? They're the ones, they still, if the covers is a pairs of electrons, then there you go. The person who's always snatching the covers is the one that is more electronegative. And HBr the polarity is going to go this way. It's easy. This one is simple because bromine is much more electronegative than hydrogen. So this one is a polar molecule. So it's going to be it's going to be polar, non-polar, polar, non-polar, non-polar, and polar. All right. Now you just think that your boyfriend complains about you being electronegative. Absolutely, Gabby. That's the best way to think about it. All right, let's do one more question before we get out of here. Let's do one on intermolecular forces. And here we go. So once again, it's all about shape. It's all about polarity before you can consider what the intermolecular forces are going to be. Here we have NH4. We have the structure of NH4. It's a polar molecule, but because it has nitrogen-hydrogen bonds, it's going to have hydrogen bonding as its major types of forces. Acetone is going to be a polar molecule. We've got this oxygen atom that's up here that is pulling electrons in this direction. So being that it's just a polar molecule, it's going to have dipole-dipole forces. There are no hydrogens attached here, so this would not exhibit hydrogen bonds. And BH3, all of the bonds are nonpolar. Anyway, this is a symmetrical molecule, so the molecule is nonpolar, and we would end up with only dispersion forces for this.